Welcome to Lecture 15C on Eigenbases, Diagonalization. Last time, we talked about an algorithm to find an eigenbasis for a matrix or determine that it does not have an eigenbasis. First, we find the eigenvalues of the matrix by factoring the characteristic polynomial. And then for each eigenvalue, we find a basis of the eigenspace corresponding to that eigenvalue. This is the same as finding a basis for the kernel of the matrix A minus the eigenvalue times the identity matrix. And then we put all vectors together from the second step into one set. If there are the same number of vectors as the width of A, then that set is an eigenbasis. If there are fewer than n vectors, then no eigenbases exist for that matrix. It's also possible to determine whether a matrix has an eigenbasis without actually finding one. So without actually going through this algorithm, we can check the dimension of each eigenspace of the matrix and then take the sum of the dimensions and check if that is equal to the width of the matrix. If not, then the matrix does not have an eigenbasis. Another thing that works, but only if the matrix has n distinct eigenvalues, is that we know that a matrix with n many distinct eigenvalues must have an eigenbasis. If the matrix has fewer than n distinct eigenvalues, then we have to do more work. We have to either use this or we can just go back to the algorithm and try to find an eigenbasis. Last time, we also talked about how eigenbases can be used to simplify multiplication. This can be encoded into a special factorization of a matrix. This is called a diagonalization of A. Let's start with a computation. Suppose I know that a square matrix has an eigenbasis. The vectors are denoted by V1 through Vn. By definition, S is a basis for Rn. Let me now take a concatenation of the vectors in S, call this matrix P. Then P is an invertible matrix, and that is because S is a basis for Rn. I can then multiply P with A on the left. And when I do that, that is the same as replacing each of the columns of P with the matrix A times the column vectors. This is true in general. If I have two matrices, B and C, then taking the product BC would give me a matrix where the column vectors are exactly B times the first column of C. So this would be the first column of BC. And then the second column of BC would be B times the second column of C, and so on. But remember that S is an eigenbasis for A. So each of these vectors is an eigenvector for A. That means A times V1 is equal to some number times V1. And A times V2 is equal to some number times V2. So here the numbers lambda 1 through lambda n are the corresponding eigenvalues for the eigenvectors V1 through Vn. Note that even though I'm using different labeling for the lambdas, they do not have to be distinct. So it's possible that lambda 1 and lambda 2 are equal. When a matrix is of this form, you can factorize this matrix in this way. I can put the numbers lambda 1 through lambda n as the diagonal entries of a diagonal matrix. And on the left, I get back the original matrix P. So this matrix here is equal to this matrix, the concatenation of S times the diagonal matrix, where the diagonal entries are the eigenvalues. Call this diagonal matrix D. This means that I have A times P equals P times D. And I can rewrite this so that I can have a formula for A. So if I multiply on the right by P inverse, I get that A is equal to P times D times P inverse. This formula is what is called a diagonalization of A. Whenever you have an eigenbasis for A, you can always have this diagonalization. So a matrix with an eigenbasis is called diagonalizable. Note that a diagonalization of a matrix is not unique. It depends on your choice of eigenbases. Here are some examples. I have this 2 by 2 matrix A, and on the right is one possible diagonalization of the matrix. To get this, I first find an eigenbasis for A, and in this case, the two vectors in the eigenbasis are these two vectors, and the number 1 is the eigenvalue corresponding to this first vector, and the number 4 is the eigenvalue corresponding to this second vector. And this matrix is just the inverse of P. This is another example where I have a 3 by 3 matrix. I find all of the eigenvalues. This matrix has 3 distinct eigenvalues. So without even finding an eigenbasis, I know that the matrix does have an eigenbasis. And one possible eigenbasis would be if I take the set of these 3 vectors. And again, this matrix is just the inverse of P, and you can find that using the method we have learned before by row reduction. So note that P and D really depend on the ordering of the eigenvalues. So here I have to put this first vector here if I want this number 3 to be in the first column here. So if I want to switch it so that instead of this D, let's say I swap this 1 and 2, then I also have to swap the placement of these two vectors in P. And then, of course, the inverse of the matrix will change as well. In this example, I have this 2 by 2 matrix, and I want to write it as P times D times P inverse, where D is a diagonal matrix. Before I can do the diagonalization, I first need to find one eigenbasis for A. I use algorithm 2. I find all eigenvalues of A, and then I find a basis for each of the eigenspace, and then I put all basis vectors together and make sure I get an eigenbasis. First, I write down the characteristic polynomial of A. I take the determinant of X times the identity matrix minus A. So I have the determinant of this matrix. I use the determinant formula for 2 by 2 matrix. I take the product of these two entries minus the product of these two entries. So I have x minus 2 squared minus negative 1 squared, which is 1. I rewrite it, and then from here, you can either do the quadratic formula or complete the square, or you can notice that in this case, we can factor this into x minus 1 times x minus 3. So the roots of our polynomials are 1 and 3. And so the eigenvalues of A are 1 and 3. The fact that A has two distinct eigenvalues and A is a 2 by 2 matrix is a good sign. It means A has an eigenbasis. The next step is to find a basis for each eigenspace of the matrix A. First, we find a basis for the one eigenspace of A. This is the shorthand for the one eigenspace of A. This is the same as finding a basis for the kernel of A minus 1 times the identity matrix. So I take A, 2, 1, 1, 2, and I do minus 1 times the identity matrix. So I do minus 1 here and minus 1 here, and just minus 0 at the other places. This is the same as having the matrix 1, 1, 1, 1. And from here, I can row reduce. I arrive at this row echelon form. I see that the second column does not have a leading one, so I set the second variable to a parameter. And then I can do back substitution using this equation. This gives me x is equal to negative t. So the general solution is a vector where the first entry is negative t from this x, and the second entry is t from the y. I can write it as a linear combination where t is a coefficient, and I take this concrete vector, and this will be a basis for the one eigenspace of A. After this, I find a basis for the eigenspace of the other eigenvalue of A. The other eigenvalue of A is 3, so I find a basis for the 3 eigenspace of A. This is the shorthand for the 3 eigenspace of A. This is equal to the subspace, which is the kernel of the matrix A minus 3 times the identity matrix. So again, I take A, which is 2, 1, 1, 2, and subtract that with 3 times the identity matrix. So I have minus 3 here, but just minus 0 here and here. This is the same as this matrix. So to find a basis, or first find a general solution for the kernel of this matrix, I put this into an augmented matrix form. I do row reduce until I arrive at this row echelon form. I see that the second column has no leading one, so I let the second variable be equal to t, and then this equation is x minus y equals 0. This gives me x is equal to t. So my general solution would be t times the vector 1, 1. So one possible choice for eigenbases that I can choose is the set consisting of this vector 1, 1. In the next step, I combine all vectors together. So I take all vectors from the basis of the one eigenspace. It just has one vector, which is negative 1 and 1. And I take all vectors from this eigenspace, and I put all of them together into one set. I see that this set has 2 vectors, and the matrix is 2 by 2. And this tells me that this set is an eigenbasis for A. Now that we have an eigenbasis for A, we can perform the diagonalization for A. To diagonalize A, we need these 3 matrices where D is a diagonal matrix and P is an invertible matrix. Because we have an eigenbasis for A already, it is easy to know what P we can choose. We can just take a concatenation of the vectors in the eigenbases. So I take these 2 vectors and concatenate them to have this matrix. This would be my P. To compute the inverse of P, we can either do the algorithm where we row reduce, or for the 2 by 2 case, there is an easy formula for finding the inverse of the matrix. So if P is the matrix with entries A, B, C, D, we can just compute 1 over the determinant of the matrix and then kind of change the entries accordingly. To compute the matrix P, or to compute the determinant of P, I just do negative 1 times 1 minus 1 times 1. So this gives me 1 times negative 2. And then I swap these 2 entries. And then I turn these 2 entries into their negatives. So I get this matrix. And this is the inverse of P. Computing the diagonal matrix is also easy once we know what the eigenvalues are. So the matrix D is just the diagonal matrix with eigenvalues on the diagonal. Our eigenvalues are 1 and 3. We just have to be careful that what we put in the first column here correspond to what we put in the first column in the P. So 1 should be the eigenvalue whose eigenvector is here, and then 3 should be the eigenvalue whose eigenvector is this second column of P. Now that we have computed P, P inverse, and D, we're almost done. This means that A is equal to P times D times P inverse. So I can write this A as this factorization. You can do a check where you can confirm that this product is actually equal to this product. One application of this is that if you have a matrix that can be diagonalized, then this will be helpful when you need to do a large power of the matrix. For example, let me just do a small example first. If I want to do A times A, this is the same as BD B inverse times BD B inverse. Here, B inverse and B are right next to each other. So this is equal to the identity matrix. So they cancel out. So this becomes just B, D, D, B inverse. Let's say I want to compute A inverse. We know A is B, D, B inverse. But we know that what we can do is we can take the inverse of each of these, but do this in reverse order. So first I take the inverse of B inverse, which is just B, and then I take the inverse of D, and then I take the inverse of B, which is B inverse. And in fact, you can replace this 2 with a much bigger number, like 100. And so we can compute like A to the 100 with B times D to the 100 times B inverse. And this is much faster than computing A to the 100 directly because this D is a diagonal matrix. In this example, we have a factorization of A diagonalization of A. It could be computed in the way that I explained earlier, where here is the matrix where the diagonal entries are the eigenvalues. And then this matrix is a concatenation of the vectors in an eigenbasis of A. And this matrix is just the inverse of this matrix. So as I have explained earlier, I can rewrite A squared as B times D squared times B inverse. To compute D squared is very easy because D is a diagonal matrix. We just get this matrix that is still a diagonal matrix where each entry is just D squared of the original entry of D. And then using this formula, we can compute A squared as just this matrix B times D squared times B inverse. And then the inverse of A is equal to B times the inverse of D times the inverse of B. But the inverse of a diagonal matrix is easy to compute. We have, again, a diagonal matrix where each entry is the inverse of the original number. The inverse of a number is just 1 over that number. So I have like 1/3, 1/2, and just 1 here. So A inverse is just this matrix B times this matrix, which is the inverse of D, times B inverse, which is this matrix. To compute A to the 100, you can go directly to the formula in the previous slide, or you can also derive it. Here we know that A is equal to B times D times B inverse. So if we write B, D, B inverse 100 times, we see that we have B inverse and B next to each other and they cancel. So what we would get is B times D multiplied 100 times B inverse. So this is B times D to the 100 times B inverse. We already know how to have B and B inverse from here. And we just need to compute D to the 100, but that's easy. That's just, again, a diagonal matrix where the entry is that original entry to the power of 100. So this is my D to the 100. So my A to the 100 is just this product. And this is much easier to compute than to compute A 100 times, because now I just have a product of 3 matrices instead of a product of 100 matrices. Note that 3 to the 100 here is much bigger than 2 to the 100 or 1 to the 100, which is just 1. So this matrix is close to this matrix. One of the most powerful results in linear algebra is that an important class of matrices always has a nice eigenbasis. Let me tell you a new definition. A set of vectors is called orthogonal if the dot product of any pair of vectors is 0. Note that if you think about this geometrically, 2 vectors are orthogonal if they are perpendicular to each other. Recall that a matrix is called symmetric if it is equal to its transpose. The theorem says that if A is a symmetric matrix, then A has a basis of orthogonal eigenvectors. This goes the other way. If a matrix has an orthogonal eigenbasis, then the matrix must be symmetric. This theorem has a lot of applications in other fields. In this exercise, let's just verify that the eigenbasis we found earlier in exercise 8 is an orthogonal eigenbasis. We found that this was an eigenbasis for A. To check that this is orthogonal, we just need to take the dot product of these 2 vectors. So the dot product here would just be -1 times 1 plus 1 times 1. So this gives us 0. So yes, this set is orthogonal. So this is an orthogonal eigenbasis. And note that this matrix is symmetric. In this exercise, we want to know if this matrix is diagonalizable. And let's do this without actually finding a diagonalization of the matrix. We see that this matrix M is symmetric. If we take the transpose of M, it would be equal to M. Another way to see that is we can look along this diagonal. We see that if we reflect the entries along this diagonal, all of the entries are the same. So by the spectral theorem, this matrix M must have an orthogonal eigenbasis, but for what we need, we really just need to know that M has an eigenbasis. It doesn't matter if it's not orthogonal. Any matrix that has an eigenbasis, even if not orthogonal, is diagonalizable by theorem 5. So yes, this matrix is diagonalizable.